This traffic case covers an intra-serving gateway handover with the X2 interface, meaning the UE will remain under the same MME serving gateway and the involved base stations can communicate with each other. Handover is only taking place when a mobile is in connected state. Hence, the user plane is established. A connected UE will constantly send measurement reports to the eNode B, but it is the eNode B that instructs the UE what to measure upon. It can, as an example, instruct the UE to measure on UMTS NBs instead of LTE base stations. A closer look on the measurement configuration instruction from the eNode B. In this picture, the color scheme is as follows. Red indicates what is signaled on the physical layer, blue indicates the MAC layer, and green upper layers. The measurement configuration will be carried in an RRC connection reconfiguration message sent on a physical downlink shared channel. As always, a physical downlink shared channel must be scheduled by a preceded physical downlink control channel. The measurement configuration holds threshold values for triggering the UE to send a report. The cyclic redundancy check of the physical downlink control channel is scrambled with the cell RNTI of the connected UE. As you might have noticed, the RRC connection reconfiguration message can be used in a number of different situations. If you want to learn more about this, please visit the Spec Tool chapter RRC. In the Mac PDU in this picture, there is also an example of how the eNode B sends a time alignment value to the UE. This is a Mac peer-to-peer information, hence in blue color. To an RRC connection reconfiguration message, the UE always answers with an empty RRC connection reconfiguration complete message. The scheduling grant is sent by the eNode B on the downlink, and the UE has 4 milliseconds to assemble the Mac PDU before transmitting it on the uplink. The owner of the UE has now moved into a position where the radio conditions will trigger the UE to send a measurement report. The UE will need a scheduled uplink resource in order to transmit the measurement report. A scheduling request can be sent on the physical uplink control channel to indicate that the UE needs to be scheduled on the uplink. Or, if the UE is involved in sending uplink data and already has been allocated an uplink resource, this resource can be used. When a UE has been granted uplink resources by the scheduler in eNode B, it is up to the scheduler in the UE to decide how these resources shall be used. RRC signaling has a higher priority than user data. Therefore, the UE will use the uplink resource for a measurement report. The measurement report will now be evaluated by the source eNode B, and a handover decision made. In our example, it is the lowest base station in the picture that will become the target eNode B. The source eNode B will now contact the target eNode B to request a handover. The target eNode B has the possibility to admit all or some of the services, or radio bearers, in the source cell. It also has the possibility to reject the handover if it is already suffering congestion. If that occurs, the connection between the UE and the source eNode B will be maintained as long as possible. The handover request message sent by the source on the X2 interface to the target eNode B will include The identity of the target cell. It is very common with three-sector cells, E-node Bs. It must be pinpointed into which cell the handover is going to occur. The globally unique MME ID. In a network, there can be more than one MME, and one base station may be able to signal to more than one MME. The new base station needs to know which is the valid MME for this UE. There is also RRC information in this message, here in green color, intended to be read by the RRC level in the target eNode B. You can find more information on this in the Spec Tool chapter RRC. Information about the ERABs used and established in the source cell is also included. The target eNode B has the possibility to admit none, some, or all of the ERABs. The handover request acknowledge message will include the admitted ERABs, a transparent container with information from RRC in target eNode B to the RRC protocol in the UE. This container carries a complete RRC connection reconfiguration message with information about, for example, the configuration of the random access resource in the target cell and a new cell RNTI. The target eNode B can also provide a dedicated preamble to the UE, more on that soon. The RRC connection reconfiguration message will be delivered by the source eNode B to the UE. If the handover is successful, this is the last message between the old eNode B and the UE. To avoid unnecessary retransmission over the air interface, the source eNode B will transmit the last acknowledged sequence number of transmitted and received PDCP frames. Please see the Spec Tool chapter PDCP if you want to learn more on this subject. The core network is not yet updated and aware of that a handover is to take place in the access network. Therefore, user IP packets from the serving gateway will be transmitted to the source eNode B. These packets can now be tunneled between the source and target eNode B on the X2 interface. The UE will now try to establish a radio resource in the new cell. The procedure of establishing a radio resource always begins with a random access preamble sent by the UE on the random access resource. But as described in the lesson traffic case RRC connection and attach, this is a contention-based solution where collisions can occur. If there is a collision, the UE will not get a random access response from the eNode B, and will after a while timer out and try to send a preamble once again. This second try can also experience collision. This is a handover, where time is crucial. Hence, the UE can be given a dedicated preamble. The dedicated preambles are controlled by the eNode B and are only allocated to mobiles in a handover situation. Information about which of the preambles that are dedicated and which are not is found in SIB 2. The dedicated preamble is provided to the UE, as described earlier, from the target eNode B via the source eNode B. When using a dedicated preamble, the UE will not suffer from any congestion on the random access resource, thus saving time. Information about the random access resource was also provided in the RRC connection reconfiguration message. After a transmission, a random access preamble follows, as always in the successful case, a random access response, including a timing alignment value, an uplink grant, and a temporary cell RNTI. This is the same cell RNTI as given earlier in the RRC connection reconfiguration. Earlier, the UE received an RRC connection reconfiguration message from the target eNode B via the source eNode B. The answer to this message is always an RRC connection reconfiguration complete sent on the Signaling Radio Bureau 1 on a dedicated control channel. The configuration of the dedicated control channel was also included in the RRC connection reconfiguration message. During a handover, there is no contention resolution mechanism included. Please see Chapter Traffic Case RRC Connection and Attach and the Spec Tool Chapter MAC to learn more about contention resolution. And since the RRC connection reconfiguration complete is an empty message, a MAC control message is added here to confirm that the previous allocated cell RNTI is now a valid cell RNTI. When the optional X2 interface is used, as in this traffic case, the base stations themselves are taking care of the handover. When the handover is completed, the core needs to be updated, and it is the target eNode B that will update the MME. MME will then in turn inform the serving gateway of the news. The S1AP message path switch request will include the tunnel endpoint identity and the IP address of the target eNode B. This information will be relayed by the MME into the GTPC message modify bearer request to the serving gateway. The source eNode B will be instructed by the target to release all resource related to this UE. Last, the re-established user plane tunnel.